For this lesson, we're going to start a new unit. It's really a continuation of our trigonometry concepts, but it takes it in a fairly different direction, which is why we break it off and consider it to be a different unit on its own. So we're going to start off with a look at what are known as periodic functions. Now, the idea of periodic, it's something that repeats itself in a regular pattern that can be identified. Each of those repeated patterns is known as a cycle, and I'm going to illustrate each of these definitions as we go. One cycle, this is where we get the word periodic, or the two are related. A single cycle, which we measure normally, we will put some sort of measurement along the horizontal axis. So whatever the length or the duration of one cycle, that is known as the period of the function. So you can have many cycles in the function, but the period is a single value that is being repeated over and over again. Now we also, from a graphical point of view, there are a couple of other considerations that we want to take a look at. One of them is the axis of the curve, and this is the horizontal line that runs through the middle of our periodic or cyclic graph. And when I say the middle, I mean it's halfway between the maximum and the minimum. And that's essentially borne out by this very simple formula. It's kind of like the midpoint formula from geometry. So we've got the maximum, the minimum, we add them together, and we find the middle value between the maximum and the minimum. What makes this confusing is that there's another formula for finding something called the amplitude, and the amplitude is basically the total distance from the top to the bottom. And so the way we find that is we take the maximum value minus the minimum value divided by 2. Now these formulas are all well and good, but to be honest with you, you are generally, unless you're only given algebraic values, unless you are not given access to a graph, in general you're going to want to think about these things in terms of the graph first, because if you can understand them in terms of the graph, you can usually figure out what they're supposed to be, and it will help you keep these formulas straight. So let's take a look at a graph of a periodic function. So you can see it is a function. This passes the vertical line test, but it's not something like anything we've come across so far in the course. So I ask for a couple of things here. Identify a cycle, identify the axis of the curve. I'm actually going to draw that in. And what is the amplitude of this periodic function? So to identify the cycle, we are looking for something that repeats. So we've got this jagged, this is known as a sawtooth wave or a sawtooth function. So what I've done is I've selected the highlighter, and if we start here, then to identify a single cycle, we're looking to see when do we get to a point on the graph where the graph is going to start to repeat itself. So if I travel along this part of the graph and then I get to here, so let's pause here. It's now back at the same y value, but the graph is not repeating itself, because when I was at this y value, I was going up and to the right, and now at this y value, I'm going down and to the right. So the graph is definitely not repeating itself yet. So we have to continue. We haven't found a single cycle yet. So we keep going from there down to the minimum, the lowest point, and then we start coming back up again. And it's when we get to this point where once again we're crossing the x-axis, but now you can see I'm about to start repeating a second cycle, which I could draw or highlight like that. So there's my first cycle, there's my second cycle, and so I've identified, in this case, I've identified 2 cycles. What about the axis of the curve? Now the axis of the curve is going to be a horizontal line, so let me just go ahead and get a horizontal line, but I'm actually not going to locate it yet. I'm actually going to, I'm just doing something here. So now I'm going to shift that line. And you can probably see quite easily, where am I going to be where I'm halfway between the maximum and the minimum. And you could just try out some, and you very quickly will settle on this value, which is y equals 1. And so there's my axis of the curve. The axis of the curve is y equals 1. And sorry, I think I've cut off part of your screen there. Is that? No, it's visible. Okay. So the axis of the curve is at y equals 1. And as far as that formula goes, it's the, let's just jot down a couple of additional things here. The maximum value on this graph is 4. The minimum value on this graph is -2. And the formula for the axis of the curve is y is equal to the maximum plus the minimum divided by 2. So that's going to be 4 plus -2 divided by 2, which is equal to 4 minus 2 is 2 divided by 2, which leads us to the axis of the curve, which is y equals 1. Similarly, without going to the formula first, well, what about the amplitude? The amplitude is basically measuring a distance. It's measuring the distance from the maximum to the minimum. So once again, if I were to maybe put that on as a vertical line, my maximum value was at 4, my minimum value, so my maximum value is at 4, my minimum value is at -2, and so this is the amplitude. And you could count that off. You can see the amplitude is equal to 6, but if I wanted to figure that out, now sometimes we use the symbol for very good reasons. We use A for the amplitude, but it's very easy to confuse that with the A value that we use for vertical stretch, for vertical compression, for vertical transformations. So you can use it, and I will probably be caught using it as well. It would be more appropriate to use absolute value of A for the amplitude, because the amplitude is a distance, so it's always going to be positive. And it's going to be the maximum minus, sorry, I actually gave the total distance there, didn't I? The amplitude is not from top to bottom, it's half of that. So I need to delete that and get my eraser. So the amplitude is absolutely not 6. The amplitude is instead from the middle, from the axis of the curve to the maximum, which is 3. Or we could also represent it from the middle to the minimum, which is, once again, 3. Whether you measure it from the top to the middle or the middle to the bottom, it's still going to be an amplitude of 3. And now the amplitude is equal to, and so in this case we use the subtraction formula, 4 minus -2 divided by 2. 4 minus -2 is 6 divided by 2. And so we end up with our amplitude is 6 divided by 2 is equal to 3. So those are those 3 properties. Now one thing I haven't addressed yet is the period. Now you can probably take a look at it. It's on there, but I've just got that separated off into another page. So I've got the clean graph again. What I am going to do is I'm actually going to put back that first cycle that I had highlighted, just for reference. And now we ask ourselves, well, what is the period in this case? And the period is the horizontal length of one cycle. So we started here at -2, and we started repeating again at 3, so you can just do the math there, or you can get it from your graph And you can see that in this case, we've got 5. Now, quite often, your period could be a distance, centimeters, meters, kilometers. It could be time is very common, seconds, minutes, hours. But for now, it's just 5 units because I have not assigned any units. So the period of this function is 5 units. So there's your basics of a periodic function. Those concepts are all you need to start. You can start to analyze the graph from there. So let's continue with that. Now that I've got an idea of where a cycle is, and again, I'm just going to keep that very prominent. So there is one cycle, and then it says to draw an additional cycle on the graph. Now, since we know that the period is 5 units, if we take a look at the graph as it stands, well, my x-axis from -2, it only goes to -5. But if I need 5 units, I need to go back to -7. So it's not visible there. From 8, if I add 5 units, well, that takes me to 13. Oh, that's going to fit just fine. So there's a couple of ways you could do it. You could just basically, particularly if you had a ruler, you could take a straight line and you could extend this, just being very careful to extend it along the same line or slope. And now this one, not as easy, right? Because you're not continuing a straight line, but you could probably get away with it. You could probably eyeball it and realize that that one is lined up. And finally, the last little piece goes there. Okay, that's one way you could do it. Another way you could do it is making use of the idea of the periodicity, the fact that this is repeating. If we take a look, for example, take a look at this point. This is the point 2, -2. Where does that point repeat again? It repeats here at 7, -2. If we take a look at the x values, notice 2, we started here with 2, we added the period, and that gave us 7. So now if we start here at 7, and we add the period, that gives us 12, and sure enough, there is a point here at 12, -2. So we could have also done another period that way, using key points. I could have, for example, I could have taken this point, and you don't have to write it out, you could have done it in your head. This is the point 5, 4, which means I'm going to add 5 to that, which should take me to the point 10, 4, which of course it does. And because this is made up of straight lines, once I get a couple of points in place, then everything's taken care of. This is the point 8, 0, and it's going to take me to the point 13, 0. So there are a couple of ways that you could go through this to accomplish it, but the concept remains the same. Okay, for the given periodic function, we've already done a little bit of this because I reordered things a little bit. So the maximum value, as we already talked about, the maximum value is 4. The minimum value is -2, and the amplitude goes from the axis of the curve, which is at 1. The amplitude goes from the axis of the curve to either the maximum or to the minimum. So we could say the amplitude is 3 units from the middle up, or we could say the amplitude is 3 units from the middle down, but either way, the amplitude is positive, and in this case it's positive 3. Okay, so now let's stretch it a little bit further. I'm going to be making use of function notation, and I'm also going to start to, beyond the kind of simple concepts that we've looked at already with periodic functions, I'm going to take that a little bit further and stretch things. So I ask, well, what's f of 12? Now, I've gone back to the original graph. So even though I had graphed this before, so on a previous page I had graphed a third cycle, I've taken that away for now. Now, if I kept the third cycle, we can find the answer to this very easily. F of 12, here is the x value of 12, so we can see the answer is -2. But conceptually, what I'd like to make use of is the idea that, wrong page, f of 12, what we want to do, what we want to become comfortable with, is relating. So basically, we want to take this and we want to relate to a point on the graph. Okay, so we want to relate this f of 12 to a point on the original graph. And the way we do that is, when I showed you how to extend the graph, we're going to do that now in reverse. So I'm curious about this value of 12, but I know that this graph is periodic, and I know that it has a period of 5. So what happens if I take 12 and I take 5 steps backward? 1, 2, 3, 4, 5. That means that whatever is happening at f of 12 must also be happening at f of 7. And that's the key to this. That's what I really wanted to bring home about this particular part. Whatever is happening at f of 12 is the exact same thing as is happening at f of 12 minus 5. And I just want to emphasize that 5 is the period. I can actually add or subtract as many periods as I want to, and I should end up with the same value. So for example, from this 7, if I step back 1, 2, 3, 4, if I step back another 5 steps, not surprisingly, those values should all be the same. And so f of 12 is the same as f of 12 minus 5, which is f of 7. But we could also say that's the same as f of 7 minus 5, again, focusing on the period there, which is f of 2. Now, I didn't need to go that far, but in both cases, what is f of 7 and what is f of 2? Both of them have a y value, which is the value of the function, of -2. So f of 12 is actually equal to -2. What would I be looking for? Probably I would be looking, if you wanted to put this step in, you could, but I'm probably looking for you to recognize that f of 12 is the same as f of 7, and then go to your answer from there. Same idea here. What is f of -4? Let's change the color. There's -4. It's not on our graph. Yes, we could draw some or all of another cycle, but instead 1, 2, 3, 4, 5. And that would put it at the same value as f of 1. So f of -4 is the same as f of -4 plus 5. Once again, adding the period, which is the same as f of +1, and f of +1 is equal to 1. Now, hopefully that sits okay with you, so let's take it a little bit further. What if I asked, what's f of 35? Yes, we could go through this manually. We could, since we're on the high side here with 35, I could actually go, I could take 35, let's do that over here in rough work. I could go 35 minus 5 equals 30, minus 5 equals 25, and I could count down from there, 20, 15, 10, and finally we get to 5, and 5 is on our graph. So our answer to the first one is going to be here. It's going to line up. So f of 35 is the same as f of 5. And we could do that through what we would call a brute force method. can we do something a little bit more elegant? What we can do instead, what I did here, these jumps were basically I was jumping by one period at a time. So instead of doing it that way, why don't we figure out how many periods there are in here? Because we know our graph lives around the origin. So if I can get myself down to maybe this something on this first graph or even the second graph, that's even better. So the number of periods, how many periods are in 35? Well, I would take 35 divided by 5, and it turns out that's a nice clean number. That's 7. So what I can do now is I can say that f of 35 is the same as f of, now this is going to get a little, since I'm on the positive side, I'm going to subtract 7 of those periods from that value because there were 7 periods in here. And of course, that's just f of 35 minus 35, which is f of 0. And we found that out. We figured that out graphically. Actually, we didn't go quite that far. We went down here to 5. But of course, f of 0, which takes us right down to the first cycle, has the same y value as f of 5. And the answer to that is 4. Rather than going through this brute force method at all this time, why don't we look at the same thing here? Let's take the number 71 and divide it by 5. So it turns out that 71, now there's a couple of ways you could do this. If you went to a calculator, you would end up with 14.2. So the key that we want to use here is only the whole number of periods. So that would be one way that you could do this. So we could then say that f of 71, so this is me doing it the exact same way I did over here, is the same as f of 71 minus, and now I'm going to subtract 14 whole periods, which ends up being f of 71 minus 70, and that's f of 1, and from our graph we can read f of 1 directly. F of 1 is equal to 1. And that is method number, let's call that method number 1. Or we could have said that 71 over 5 is equal to 14.2. And so now what I'm going to do is I'm going to take the 0.2. This one's a little bit, you have to have a pretty deep understanding to do this comfortably. So now I take 0.2 times the period, and it turns out that 0.2 times the period is equal to 1, which means that f of 71 must be equal to f of 1. You could do it either way. I think the first way I showed you is the simpler way, that's why I'm emphasizing it. But if it occurs to you, if you can see that, then there's an option here as well. Okay, moving on. All right, let's put it to a little bit more of a practical purpose, and also this is leading into how we're going to start to tie this into trigonometry. A Ferris wheel is a circular amusement park ride, and there's something very special about what you get when you do circles like this. They tie in very strongly with trigonometry, and we'll be making that connection in a future lesson. So here we have a Ferris wheel that has a diameter of 60 meters. So that means from the highest point to the lowest point is 60 meters. It stands 5 meters above the ground. That means from the lowest seat to the actual ground is 5 meters. As it rotates, the height of a particular seat above the ground is changing. Sure, if we looked at these people and I'm just arbitrarily choosing, I'm choosing the direction that it looks like they're facing to me, they're going to start at a maximum and then they're going to go down to a minimum and then back to a maximum again. It takes 1 minute for the wheel to make one complete revolution. And that's telling us that the period is 1 minute. Pick a seat and graph its height as a function of time. So we're just going to do this roughly to begin. And since I started with that top seat, I'm going to start there again. To do this graph, technically you could pick any seat. It's just the graphs can be more or less complicated because of it. So if I start on the top seat, those people, actually I've already made a mistake. I just want to go back and check the Ferris wheel has a diameter of 60 meters and the Ferris wheel itself stands 5 meters above the ground. So what is the height of that top seat? And the answer to that is, of course, 65 meters. So that top seat is going to be, so that's 70, so it's about halfway in between. So the top seat starts there at 65 meters. It takes 1 minute for a complete revolution, which means after 1 minute, that top seat is back where it started. Now, you can see a very faint Ferris wheel in the background here. Well, if it takes 1 minute for them to go all the way around, then it must take 30 seconds or half a minute for them to get to the bottom. And the bottom is 0.5 meters above the ground. So that's at half a minute. And then it's going to take a quarter of a minute for them to get to the middle here. Now, as far as these calculations go, and maybe this is one that's worth doing, because the middle is going to be the axis of the curve. So the axis of the curve is the, if you remember it, it's the max plus the min divided by 2. So the maximum in this case is 65 plus the minimum, which is 5, divided by 2. That's 70 divided by 2, or 35. So that means that at 1/4 of a minute, or 15 seconds, we're going to be at 35, halfway between 30 and 40. And at 3/4 of a minute, we're going to be halfway between 30 and 40. And now here is, and it's a perfectly reasonable thing to do, a lot of people at this point, they do something like that. It's kind of like that sawtooth we looked at before. But I want you to imagine, try to put yourself in the position of the person being on this ride. What would it feel like to get to the bottom there with a sharp point? Because remember, it's moving through here. So it turns out that a curve like this would not look this way. It doesn't actually have hard straight lines. It's a curve. And the way that I normally think of it is, well, when you get to the bottom of a Ferris wheel, it kind of smoothly transitions into going down and then going back up again. So at this bottom part, you need a curve that looks like that. At the top, you need a curve that looks like that, and a curve that looks like that. That takes care of those smooth transitions. And this is going to be very challenging for me to do with the tablet. And you just do your best to draw a curve that follows and honors that smooth motion throughout. And so there we have a single cycle of the motion of the person from the top of the ride. That looks quite different, but also bears some similarities to, what about the person who started at the bottom of the ride? They started here and they ended there at the bottom. And then in the middle of the ride, they were at their highest point. And it turns out that at 15 seconds and 45 seconds, they also were through the middle. So again, I'll just put a curve in advance. I butchered that. and that too. I won't delete the whole thing. I'll give myself one more try. And then I will call it quits. Let's go from this direction. Okay, not perfect, but it will do. Okay, so there we have an example of two looking quite different, but also they share some similar features. I'm just going to put it on here just for labeling. Since we calculated the axis of the curve, that's our axis of the curve, y equals 35. Okay, that's it for this lesson. There is a class activity on the next page, which I'm not going to do as part of the video, and some assigned work, which I think is up to date for our current textbook.